Okay, so we're going to start with the last topic in the course, and that is soil and vegetation. Um, so what are soils? Let's start with the basic definition of what soils are. These are defined as unconsolidated geologic material that is located at the surface of the Earth's crust. It's generally within the top 2 meters. The entire formation of soil, which is a long drawn process, is called pedogenesis. So, how is soil formed? Soil is formed because of the interaction of climatic factors as well as the vegetation that grows on it. And soil and vegetation are interlinked. For example, a particular type of soil will support only a specific type of vegetation, and that vegetation in turn will determine the nature of the soil. And the climatic factors are responsible for the nature of soils and vegetation together. In terms of the role that soils play in our daily lives, they are a part of everyone's daily life. For the first major role that they play, we know that they're all essential for agricultural productivity. They provide a support medium for the plants to grow, and every bit of food that we eat is basically dependent on soils. So these soils are also going to be regulating the passage of water as well as nutrients that will support agricultural productivity. They also serve as a habitat for organisms. So every soil, no matter which part of the world you're in, is an ecosystem in itself. So these are often self-sustaining ecosystems. They serve as habitat for not just one or two species, but several species which are interdependent and which also support agricultural productivity. And finally, last but not the least, it's an engineering resource. For those of you who are from a civil engineering background, you know that soils are an important building material, and an understanding of soils and their nature is very important for building foundations and so on. What are the environmental impacts? So basically what I've said already is noted over here as well. The availability of nutrients and water for plant growth is determined by soil texture, whether it's fine, whether it's coarse, what is the nature of soil, what is the hydraulic conductivity of soil, what is its porosity. All of this is determined by the vegetation that grows over there, as well as the passage of water and nutrients will determine the nature of vegetation. That's why the first slide shows you the intimate relationship between soils and vegetation. We come to buildings. Buildings and other structures are affected by the nature of soil. If you have soft soil, you can't have a normal foundation. You have to have a different kind of foundation. So all these things will determine the nature of the structures that you build on different types of soils. I've already mentioned that soil ecosystems are self-sustaining, often it's self-sustaining ecosystems, and they are location specific. So soil ecosystem in cold climates is going to be very different from soil ecosystems in warm climates or tropical climates. And these are an important habitat for organisms, whether it's microbial organisms or higher organisms. These will in turn bring us back to soil productivity, to agricultural productivity, because these ecosystems determine the recycling of nutrients. We haven't had time to cover biogeochemical cycles, but I will mention at this point that the nutrient recycling that happens in nature through biogeochemical cycles is mainly because of soil ecosystems. Soil ecosystems have a major role to play in biogeochemical cycles. Let's take a look at some of the factors that affect pedogenesis or soil formation. So I'll just show you a graphic over here to show you the different horizons. Um, this is basically a cross section into the subsurface depths to show you the different parts of the soil horizons. And at the bottom, you have what we call parent material. This is the bedrock. The weathering of this bedrock is going to result in the formation of soils. And the remaining layers on top of the bedrock are literally layers of the soil. Okay, we'll come back to this in more detail later. But that is the parent material. So the V or R horizon that I just showed you in this cross section is the original source of the soil material. And weathering of this material results in the generation of all soil. The next important factor that determines the nature of the soil is climatic factors. Out of the climatic factors, the first most important thing is rainfall and the second is temperature. So let's take a look at rainfall. What does rainfall do? When you have precipitation on any surface, on any land surface, what it will do is it will dissolve some of the minerals that are part of the parent material as well as the other layers on top. So there is leaching of minerals. This is the loss from the top layers into the bottom layers. So if I show you this graphic, whatever is at the top is exposed to precipitation. The minerals that are leaching out from the top are infiltrating into the subsurface to varying degrees, and they will reach into the subsurface layers. And those are the different horizons. Wet deposition of particulate matter and minerals from the atmosphere is the gain. So anything that is present in the atmosphere will come down with precipitation, and the minerals from the atmosphere will be the gain into the soil uh, materials. Okay, so that is rainfall. And then we know about temperature. Temperature, you already know this, is because of contraction and expansion. Let's say your daily cycle, you have heat in the daytime and cooling off in the night time, and because of that you have contraction and expansion of the materials, the physical material. So that is physical weathering, which you must have studied in high school and so on. So the next thing is chemical weathering. You already know that rainwater is slightly acidic. It has a pH of around 5.56. Currently the pH is around 5.56. So it's slightly acidic. Now this acidic material, when it falls on this rocky, weathered material, it will release and dissolve some of these minerals that we have already seen in the previous factor. So that is chemical weathering. So the minerals will dissolve due to exposure to different temperatures and as well as due to acids from rainwater and so on. Okay. Um, Then we come to organisms. How do organisms modify soils and how are they related to the soil formation ideas? So microbes are bacteria, fungi, algae, small animals, higher organisms like earthworms, snails, insects. All of these are inhabiting the soil ecosystem of any particular place. Always remember that all organisms, whether they're microbes or higher organisms, modify the environment. It's not just human beings that modify their own environment, but all organisms, by their very nature, modify their environment, both chemically as well as biologically. One, because of the metabolic processes, and two, because they excrete certain materials. So it's all part of life. And the very act of both ingesting as well as excretion is modification of the soil environment. So digestion of organic matter, breakdown of minerals by acids generated during digestion, all of this will determine the nature of soils. I'll come back to this point in a little more detail. Topography is another very important factor. So weathering at higher altitudes is generally much greater than weathering at lower altitudes, simply because you have high velocity winds at higher altitude and low velocity winds at lower altitude. So that's one simple factor. Variations in temperature, variations in precipitation, all of that, if they are related to elevation, that will also modify the nature of the soils. Another simple example of topography is leeward versus windward. There is, let's say you have some hills or mountains and you have a windward side, the one that's facing the wind, and you have the leeward side, which is against the wind, which is protected from the wind. The soil on both sides is going to be different because of the rate of erosion, even though the parent material on both sides is the same. So the bedrock material is the same. But because of erosion rates, which are related to wind velocity, that will determine the change in soil texture. So the fineness, coarseness of the soil will determine the nature of the soil. Then we come to time. How does time determine soil formation? The older the soil is, the finer it's going to be, and you will also have a greater percentage of organic matter. That's a very important point. It's a very important difference between young soils and old soils. A soil becomes richer as it becomes older. So mature or older soils differ from younger soils because they are finer. Their ability to retain organic matter and water can be higher, and the young soils have more parent material while they have less organic matter. And remember that organic matter is very important because it helps in the soil's ability to hold on to water as well as nutrients. Without organic matter, let's say you have a young soil which has more parent material and less organic material. Its ability to hold water and nutrients is poorer compared to older soil. Okay? So older soil is generally richer and more fertile. Then we come to some other processes that affect soil formation. You have calcification. Calcification is removal of salts, especially um, removal of salts other than calcium and magnesium. So calcification means an increase in the amount of calcium and magnesium in the soil. That's one. Then you come to salinization. Salinization is something that happens where you have over irrigation of the land. So when you add too much water, remember all water has some amount of TDS. The TDS can vary, it can vary enormously. But because of evaporation in arid and semi-arid conditions, you get accumulation of salts on the surface. And if you observe it, sometimes you see soils which have a whitish color to them. And if you get a chance to look at them closely, you will find that they're white crystals of salts that have deposited on the surface of the soil. So that is called soil salinization. And in India, this is a major problem because uh, irrigation has made water available to areas that did not have enough water. And because of that, you get over irrigation and you get accumulation of salt. So the problem with salinization is it reduces the productivity of soils in the long term. Finally, laterization. Laterization is accumulation of iron and aluminum in humid tropical environments. Where we live right now are typical environments in which iron and aluminum get accumulated over a long period of time. So that's an example of lateralization of soil. All these three factors, calcination or calcification, salinization, lateralization, all three reduce agricultural productivity. We now come to soil composition. Soil composition is shown in this graphic where you have, in general, soil will have about 25% water, 25% air, mineral particles are about 50%, 45% in this case, and organic matter can be 5%. Now, these are very generalized numbers, these are not specific numbers. You can have numbers ranging from anywhere from 1% organic matter to 10%, 20%, and so on. Okay? This is just hypothetical soil composition. Out of the organic matter, the bulk of the organic matter is humus. Humus is decayed vegetation. So if you think about what is soil, you have a lot of decayed leaves, grass, all that kind of material. And as it decays, it becomes humus. Humus is this black colored um, material that looks like peat or moss or humus. These are the words we use to describe that decayed vegetation. It's black in color. It's always dark and black in color. And it's highly moist and it literally crumbles in the hand. That kind of thing and that kind of material is called humus. The remaining is vegetation, roots of vegetation and organisms that occupy the soil environment. Then we come to soil horizons. Soil horizons, you have the okay. So we'll start where I stop. These are the soil horizons. So we'll start with the O horizon. The O horizon is organic matter. And what you see at the top is the loose leaves and the organic debris that generally collects on the surface of any area, vegetated area. And just below that, you get partially decomposed organic matter. So this is the O horizon. Below that, you have the A horizon. The A horizon is the zone of leaching. Now, this organic matter in the O horizon is leaching material, both organic as well as inorganic. And the first thing that you see is a very dark layer. A1 is a very dark layer. It's rich in organic matter. The darkness literally comes from the humus-like material, which is leaching into the depth. A2 is lighter. It's inorganic material. It's mineral content, and it is much broader as well as lighter in color. A3 is the transition zone to the next horizon, which is the B horizon. The B horizon is the zone of accumulation. Now here you get accumulation of whatever material is coming from the top, both O and A horizons. And B1, A3 are the transition zone. B2 is the accumulation of colloidal material. And colloidal material, just to define it over here, any particulate material, it may be organic or inorganic in nature, anything that is below 1 micron in size is considered colloidal material. So it can be organic or inorganic in nature. So this is the zone of accumulation where all this colloidal material accumulates. B3 is the transition to the C horizon, which is followed by weathered bedrock. And the C horizon is the weathered bedrock, and D horizon is the bedrock itself. And this bedrock is the parent material for all of the rest. Okay. Let's come to another point in soil formation, and that is soil, climate, and vegetation. So, in the first graph, what you see is the depth of soil. Remember that the top soil, the layers of soil that I just showed you over here will vary in depth from one place to another and for different climatic conditions. Remember that climatic conditions are key to the development of soil. So let's take the second part of this graphic. In the tropical region, temperature is high throughout the year. Because the temperature is high, you get more weathering, so you have more physical as well as chemical weathering, and the amount of soil that is formed is much deeper. So the depth of soil and the depth of the parent material is less. Depth of soil is more, depth of parent material is less. What does that do in terms of supporting vegetation? In terms of supporting vegetation, you get much higher vegetation because temperature is higher. In general, that's associated with higher precipitation unless you're in the desert. We'll come to that next. But higher temperature, higher precipitation will result in more vegetation and greater depth of soil. Then we come to the desert, where the temperature remains high, but the precipitation is less. So because of that, your net weathering is less. The topsoil is much thinner in comparison to the tropical regions. Let's say you compare the Amazon forest, rainforest in the first case with the Thar Desert or the Sahara. If you compare with these regions, what you will see is that the topsoil is much thinner There's very little content in it. Organic content is almost negligible. It's not enough to support vegetation, so you have very, very little vegetation in the desert regions, and your temperatures are moderately high compared to the tropics. Then we come to the temperate zone. The temperate zone has low temperatures, low to moderate temperatures, and you get more weathering of soil because of the variations in temperature and precipitation. But you also have a topsoil layer which is less than, I'm sorry, the other way around, which is more than the desert and less than the tropical rainforest type region. And finally, we come to the cold desert. In the cold desert, the temperature is very low, vegetation is also low, and the parent material is going to remain high with the topsoil remaining extremely thin. When it comes to weathering of soil, I've already mentioned there are two major factors, physical weathering and chemical weathering. The result of these two types of weathering processes is that you get three different types of particles which we define on the basis of size. So we have clay, silt and sand, and clay is defined as particles with less than 2 micron size, silt is 2 microns to 60 microns, and sand is about 60 microns in size. From these three types of particles, you can get the soil texture triangle. So in the soil texture triangle, you have clay at the top. You can see clayey soil would be mainly clay material. So 50% or higher clay content with different mixtures of silt and sand. So that is defined as clayey soil and clayey material. At the other extreme, you can see sand. Most of it is 90 to 100% is sand, followed by loamy sand. Loamy sand would have small amounts of clay in it. Sandy loam would be more sand and less loam or clay. And all these combinations will result in different parts of this triangle. So, for example, clay loam has more clay and some amount of silt and sand. Then you have silty clay loam, which is again a different mixture of silt, sand, and clay. So all these different types of soil can be defined on this particular soil texture triangle. Then we come to soil degradation. How does soil get degraded? There are many ways, many processes because of which soil degradation occurs. And some of the problems associated with soil degradation is what we are going to cover over here. So I've already mentioned that soil is the basis for crop as well as livestock production. Remember that I've talked about agricultural productivity, but livestock production also depends on agricultural productivity because if you don't have agricultural productivity, you cannot sustain cattle and sheep, goat, and all of these animals. Like that's livestock. So soil fertility will determine agricultural as well as livestock productivity. And agricultural productivity itself is determined by the amount of nutrients available in the soil and the nature of the produce. What are the problems associated with these soils? There are two issues that we're going to go into. One is overgrazing and the second is soil erosion. So we'll come back to that after we go through the next one. So let's just take a look at agriculture and crop production. What is happening all over the world in terms of crop production? There are three types of crops that are generally accounted for. One is food, which we're all familiar with. We know wheat, rice, maize, all these are common food crops. Then you have forage crops. They are called forage crops or fodder crops. And these are the ones that sustain livestock. So your cattle, your sheep and goat, all of them need to graze and these are forage crops. So your meadowland, your pasture land, all that is considered forage crops, fodder or forage crops. And then you have your cash crops. Cash crops are cotton, silk, jute, bamboo, all these materials which are not used for food purposes but for making either textiles or for other purposes that have commercial value. What is interesting to me in this particular table is the total amount of area that is available on the planet. So for the different continents and for the entire global area, what you see is total land area in square kilometers. So we have 130 million square kilometers on the globe, that is land area. Okay, and in this particular graph, which in this particular table, you get 6.3 billion people. Today we know that we are close to 8 billion people on the planet. The consequence of this is that crop area per person is reducing dramatically. As the population grows, land area remains a constant, and the amount of land available for production of crops as well as other materials is reducing. So, on a global scale, today, or not today, but at the time that this particular book was written, so that's almost, let's say, 10 years ago, this data, yes, this data is 2006. So at that time, we had 0.079 square kilometers per person for crop area, and that's about 38% of the entire land area. And just remember that because of population growth, the amount of land area available for cropping is reduced. Then we come to soil degradation. I've already mentioned that these are some of the problems associated with soil degradation. So we have soil erosion. And we'll come to the USLE equation, the Universal Soil Loss Equation. We'll cover that in detail in a little bit. What is soil erosion? Soil erosion happens because the topsoil is removed from its location by wind, rain, and temperature variations. Because of that, you get loss of productivity. This can also happen due to deforestation. It can happen due to land use and land cover changes. So if you think about what you may have studied in high school, that if you remove trees, if you remove forest cover, what happens? The soil is exposed to the above three factors: wind, rain, and temperature variations. There's no protection for the soil, which is there in a forested area. So that entire topsoil gets removed by these processes of wind, rain, and temperature change. Now, if you have fertile land, but you end up using it for constructing buildings and so on, that is an example of change in land use and land cover. So it's a loss of useful fertile land. Then we come to dust storms. Now, if you have naked soil, literally no cover, no vegetation, what will happen? When the wind blows, when it's hot, you get lack of moisture in the soil, and um, it cannot hold on to its location, and so you get these dust storms. And this is very common in India during the summer, especially arid and semi-arid regions. Dust storms during the summer are a major problem because they take away the topsoil, and it basically takes away the productivity of the soil in that particular region. And if you have flowering and drought conditions, these dust storms are exacerbated. Literally, you get more of these dust storms, and the whole vicious cycle of removal of soil from the particular area becomes more and more serious, and loss of agricultural productivity becomes a major issue. I've already said a little bit about soil salinity. It's mainly because of excessive use of water for irrigation. Now, why is there excessive use of water for irrigation? The problem is that when you have these irrigation projects, most people do not realize that over supplying of water to the land is only going to result in evaporation of that water. And all water, whether it's groundwater or surface water, both types of water contain some amount of TDS. TDS stands for total dissolved solids. Groundwater generally contains more TDS than surface water as a broad generalization, and therefore, because we are moving towards more and more groundwater-based irrigation methods instead of irrigation projects, we are going to have more and more salinization of soil. So the future, if we continue to use groundwater for irrigation is that we're going to have lower soil productivity because of soil salinization. Then we come to another problem, and another problem in agriculture, because remember that soils are not created in a day or two. It takes hundreds of years to create topsoil because it's a slow natural weathering process. So any process that results in the loss of this precious resource, it's almost um, it's a non-renewable resource, literally, and best management practices are needed to prevent soil losses. There are other impacts. There are other environmental impacts that are associated with soil erosion. So you have pollution of surface water bodies. Let's imagine that there is an area where there is very little vegetation, and due to heavy precipitation, which happens very often in this area, you get heavy precipitation, excessive rainfall within a short period of time. You get high intensity rainfall, and because of the velocity of the raindrops or rainfall, you will get runoff of this material directly into surface water bodies. All the excessive nutrients and sediment that is there on the surface of the land will get washed into the surface water body. So it's complete degradation of the land and pollution of the surface water bodies. This can also lead to excessive eutrophication of surface water bodies. Because of that, you will get silting of dams and reservoirs, and you will get choking of wetland ecosystems. So all these things can happen mainly because of soil erosion. In terms of pollution, how do we pollute soil? We also degrade soil by dumping waste on soil. So we have, let's say you dump municipal solid waste on open land, what will happen? Whatever is there in the waste is eventually going to leach into the subsurface, into the soil surface. So if you have heavy metals, if you have pesticides, any other contaminants that are present in waste, if you have any of these materials in the waste, they will leach into the subsurface, they will leach into the groundwater, they will leach into the soil. And all these materials will eventually bioconcentrate in the plants. So these will bioconcentrate and travel up the food chain or up the food pyramid. I've already mentioned that many of these materials will be present in surface runoff and cause pollution of streams. So all these things are likely to happen because of open dumping of waste on land. Excessive use of fertilizer is also another problem. Again, it's excessive water, excessive fertilizer, all of these will result in similar problems. A little bit more about overgrazing. I've already mentioned that grazing is also dependent on soil productivity, and that in turn will determine livestock production. Remember, livestock production is very important for the productivity of any economy. They are the bottom of the food pyramid, both logically as well as economically. So that's a very important point for all of us to remember. Under optimum livestock densities. So remember one more thing. I think I mentioned this in another topic here, under ecology. For any particular area, let's take 1 square kilometer of any particular area, assume that it's pasture land. Under pasture land, you have a particular optimal livestock density. At that optimum or below that level, the soil is enriched by nutrients. Where are these nutrients going to come from? They're going to come from fecal deposits by the animals and recycling of nutrients by both natural biogeochemical cycles as well as by these animals and their activities on that land. This is at optimum or suboptimal conditions. Pruning happens naturally because of the grazing animal, and it actually stimulates further plant growth. So as long as you are at optimal or suboptimal livestock densities, it's good for the land. At one particular point, you will find that the livestock density, if you continue to increase the number of livestock feeding on a particular unit area of land, what will happen is that the soil, if the grazing rate is greater than the rate of growth of grass, the soil is being depleted of nutrients, right? And if the soil is being depleted of nutrients, the grass is not going to come up as fast as it's being grazed upon. And once the grass is depleted, the soil is loose. And once it's loose, it will get carried away into the streams when you have precipitation or wind action. So excessive manure on this land will enter the streams as surface runoff. It will pollute the streams and cause eutrophication. So that is something that is very common in our country. Overgrazing and soil erosion as well as water pollution. These are all interrelated and uh, the cause of many problems in our country. Let's come to the universal soil loss equation. So this is the universal soil loss equation where A is the soil loss per unit area per unit time. Our SI units are tons per hectare per year. You can have tons per acre per year. Sometimes it's difficult to convert it because all the other factors are in acres, but we'll try and figure that out. What is A equal to? A is equal to R times K times L times S times C times E. So let's go through each one of these parameters. R is equal to the rainfall and runoff factor. Let me show you what that means. These are erosion rates based on wind and water erosion on cropland and conserved land. These factors are basically derived for the US, and there has been some work in India as well. There are a few papers on this idea. It has been transferred to different geologic conditions, but then it is difficult, but it's important. So I'm going to go through it. Let me show you wind and water erosion sites. So 1982 to 1997, we can see that the erosion rate has gone down due to both wind as well as water. Now, how does that happen? How do you conserve soil? So this is CRP is the conservation program that goes on in the US for soil conservation. Okay, so the R value is going to change for that reason. We have, let me check. Let's go on with the R value. The R value is for a particular location. So understanding of the precipitation in that particular location and the runoff factor, which will determine the rainfall erosion index, that R value is location specific. In fact, most of these factors are location specific. I should also mention one more point over here, and that is unit plot. Now, the USME equation depends on what is called the unit plot concept. So there is a hypothetical unit plot that is generated, and that has a fixed dimension of 5.5 feet by 72.6 feet, and a slope of 9%. The slope of 9% is extremely high. It's not very common. We are assuming that it is regularly and continuously tilled in up and downhill tillage, which means it's the worst case scenario. So anything that we do differently is going to be a soil conservation program or a soil conservation method. K is the soil erodibility factor for a unit plot. So for different types of soils in different locations, you can see the K values have been computed already over the here in this table, and these are the K values that can be used for different locations and different soils. Then we come to LS. LS is slope length and steepness factor. Let me show you that table. These are topographic factors. Slope is so the steepness is defined in terms of slope. So from 2% to 12%. 12% is extremely hilly, and more common, at least in this area, is 2% or even less. So that is our steepness factor, and across what you see is slope length. So for different slope length and different steepness levels, you have LS values. So that goes directly into the equation. Then you have crop management practices. I'll come back to crop management practices again a little bit in more detail. But for now, what I want you to remember is only three things over here. Conventional tillage, minimum tillage, and no tillage. Tillage is basically like plowing, I think. And what you have is two methods of doing it. One is that the crop residue from the previous harvest is allowed to sit on the soil, and that helps to conserve both water as well as moisture as well as nutrients. If you remove the residue from the previous harvest, what you're doing is removing the moisture as well as the nutrients. So that is, those are two conditions for each type of tillage. No tillage is no plowing, minimum tillage is minimum plowing, and conventional tillage is some degree of plowing. There is also another point that's noted in the first column, and that is crop sequence. You have soybeans, corn, those are single crops. It's well known in agricultural practice that it's not good to have a single crop on the same land for a long period of time, because every crop utilizes a particular set of nutrients. So if you alternate one crop with another crop, you get alternate usage of one set of nutrients with the other. So that is better for replenishing the soil in terms of nutrients, and for preventing the soil from getting depleted of a single set of nutrients. So here you have the first two cases where you have single crops, soybeans and corn. Then you have corn and soybeans, one after the other. Then you have corn, corn, soybeans, corn, corn, soybeans, and small grain and meadowlands. So these are some of the practices that are encouraged in both soil conservation as well as agricultural management. And there is another point that needs to be remembered, and that is that many people think leaving the land fallow for one season is very important for allowing the soil to replenish itself. So these are some of the different crop management. So these are crop management factors that are derived for different conditions in terms of plowing, in terms of residue management. So we have cover and management factors, and then you have support practice factors. So let's come to the last factor, p-values. These are p-values for two types of support factors. How do we support these kinds of soil conservation programs? So you have contour factor and strip crop factor. Let me just show you some examples of that. This is an example of contour tillage or contour plowing. So you have a land that is, I think you're all aware of what contouring is. So here the land is being plowed along the contours of the land. So if you see, the tractor is not moving in straight lines, it's moving along the contours, and the entire land is cultivated on that basis. And this is considered to be a very good crop management method because it prevents soil erosion. So this is contour tillage, and then you have contour strip cropping. Now, this is also a good example of strip cropping. What you see over here is that you have wide strips that are used for agriculture, and there are protective strips in between the wide strips. That is for preventing erosion of the soil from one band to the next band. So that is strip cropping. So you have that kind. And then the last one is terracing. Terracing is common in the hill states in India. And these are examples of terracing where you have land with a very high steepness factor. So when you have high steepness factors, you can have cropping at different elevations, and you need to have protective barriers at each level to prevent soil from one level from eroding into the next level. So this is terrace farming, which has been practiced in India for perhaps centuries, and that's about support practice factors. And cover and management factors, that's the last point. Depending on the crop stage means how old is the crop? Is it 1 week old? Is it 1 month old? What is the age of the crop? So that will determine how you manage it. Crop canopy, is it completely covering the soil? Is there no exposed or naked soil? Because that will determine how much evaporation happens, that will determine how much erosion happens. Then you have residual mulch. I've already mentioned that how you preserve the residue from the previous harvest is going to determine the amount of water and nutrients that are conserved on the soil. So these are cover and management factors. So this is our USLE. So we have all the factors and we know how to determine them for different conditions. This is an example problem that is taken from the textbook that's noted over here. And you can determine the amount of soil lost per year, annual soil loss for any given set of conditions. Here are some example problems that you can solve for yourself for different values of the factors that are mentioned in the USLE equation. I will stop at this point and hopefully you will be able to deal with this topic.